coming to our today's speaker. We have with us Jonathan Barr, or aka JBO. He is a principal security researcher at Microsoft. Over there, he works as a Microsoft Defender research architect for cross-platform. Jonathan has a rich experience in vulnerability research, exploitation, crypto analysis, and offensive security in general. On behalf of all of us, I would like to welcome Jonathan.
Thank you for the introduction. I guess we could just start. I see a few familiar faces here. Hello to all. Let me just get the slides ready. This is macOS security features and bypasses by example by me. First of all, a bit about myself, although Sakshi did a great introduction. Jonathan Barr, or JBO for short. That's my handle name on Twitter, yo underscore whatever JBO. I'm focusing on offensive security. I work at Microsoft Defender for Endpoint as the research architect for CrossPlat. That basically means that I'm focusing on Linux, Android, macOS, and iOS. But I do some Windows stuff here and there. And I also try to produce funny vulnerability names. And today, I want to talk to you as an individual security researcher. So in this talk, I will not be representing Microsoft at all. So everything here is my own personal take on things. If I show an opinion or something or share insights, that's coming from me and not Microsoft. So I don't want anyone after this webinar to come and say, hey, Microsoft did that or something. That's not the case. With that being said, let's start. I want to talk about macOS security in general. macOS is a very interesting operating system. I would say that it has a very rich historical background, and that basically makes it a very complicated system. And I would say that in terms of security, it has many security layers. Some of them are POSIX traditional, like the things that you see on normal Unix-like systems. It has a BSD-based security layer. For example, Mac ports are used as a security feature per se. And there are Apple-proprietary security layers. And in this talk, we'll be focusing mostly on the Apple proprietary ones. There are very interesting conversations about how Apple implements certain things in terms of POSIX and BSD, but we won't talk about them during this webinar. In terms of Apple proprietary, I would say that the number one focus that I usually have is on Apple entitled binaries. Basically, you have to understand the macOS ecosystem, but I would say that these binaries are signed by Apple and they have certain entitlements. They can do certain things allowed by the OS that other binaries can't do. And because they're Apple signed, you can't just fake your binary into doing these things. So I would say that these Apple entitled binaries, and we'll see a lot of them, are interesting, undocumented, and have tons of assumptions that we might be able to exploit. And one thing, I don't remember who said that exactly, but when I got into macOS, I saw this like kind of almost a direct quote that it took years to secure Linux setuid binaries. And interestingly, we still got some in 2021 and 2022, even this year. So even in Linux, it took years to make suite binaries more secure. And even then, they're not as secure as you'd imagine. And how much scrutiny do you think that Apple entitled binaries receive? And the answer is not too much. And this is what we're going to look at in these cases. So first of all, I want to talk about my first reported vulnerability, or first publicly disclosed reported vulnerability, because there are some things that are undisclosed yet, and that's a SIP bypass that I call Rootless. SIP or Rootless is a mechanism on Mac. It's called System Integrity Protection, and also called Rootless. And it was introduced very early, as much as Yosemite, so pretty old now. it leverages the Apple sandbox to protect the entire platform, even from root. So even if you run as root, there are certain things you can't do. And the idea was to keep the integrity of the operating system, well, complete, right? So even as root, you can't attack the operating system itself. And you can disable it, but only in recovery mode. Basically, there is a tool to do that, and we'll be looking at that as well. Internally, SIP is configured by two NVRAM variables. One of them is CSR active config, which is a bit mask of enabled protections. And you have CSR data that is stored in netboot configuration that we won't get into. You can't legitimately modify those without booting into recovery mode, obviously. Otherwise, you will be able to just bypass SIP. And the tool that I was referring to, the thing that lets you turn off SIP, is called CSR util. As I said, in recovery mode, you're able to disable SIP with CSR util, but in non-recovery mode, you can do very limited things. The most obvious thing to do is to get the status of CSR util, the status of SIP. In this case, you can see that I write CSR util status and I get the fact that SIP is enabled. And if I do CSR util disable, it will even tell me this tool needs to be executed from recovery OS. So just internally how these things are working. And the CSR active config, the thing that I was referring to earlier, as I said, it's a bit mask and it controls SIP protections. And interestingly enough, you can find those in the XNU source code. And you can kind of guess even without understanding exactly what's going on. And basically compromising any of these is considered a SIP bypass and actually compromises the entire SIP protection. For example, CSR allow task for PID, this thing right here, allows you to do the equivalent of open process on Windows or tracing a process in Linux. So task for PID is basically the way for you to get a handle to a different task or a different process. That's just an example. And there are many other things here as well. So these are the bits that are actually saved inside this bitmask NVRAM variable. Interestingly enough, the number one noticeable protection in SIP is the fact that you can't modify certain files on the file system. So even if you run as root, you won't be able to modify, let's say, operating system binaries. And how are these governed? Basically, there are certain files that are restricted, and a file is restricted if it has one of these, right? The most obvious one is that it has a com apple rootless extended attribute, and you can view them with ls-lao. The capital O here will show you if a file is restricted, and then it will tell you restricted, or if it's not restricted. So that's one important thing to know regarding SIP. And there are other files that are just protected just because they're mentioned in some configuration file, this file in particular, and it's not whitelisted. So there is kind of a whitelist that overrides the files that are saved here. And obviously, you can't manually make a file SIP protected, right? If you could, then it would mean that you basically will make an undeletable malware or something. So you can't add this extended attribute to a file, even as a root. And as I said, you can view those with ls-lao. And SIP is pretty interesting because it might stop malicious operations. And it's always interesting to examine the sandbox log because SIP is basically based on the Apple sandbox. And here you can see an example, me running as root, trying to copy a plist file, malware.plist, into system library launch daemons. Now, because it's under /system, it will be protected, and it will give you operation not permitted, again, even though I'm running as root. And now, if you look at the log, you see here that I write log show, whatever, and then I look for malware.plist, it will even say, deny files, file write create in this particular path. That and if you see here, it says sandbox, but it comes from kernel. That basically means that it's zip. So it's always interesting to look at these at the log if you get operation not permitted. Now we come to kind of a problem, because how does Apple handle upgrade situations? So let's say you have an OS upgrade and Apple needs to actually override these exact paths, right? So what do they do? So apparently what they do is that they have a set of entitlements for completely bypassing SIP checks. And all of them begin with com.apple.rootless prefix. There are some of them, and they became more fine-tuned and fine-grained with time, with every major Apple macOS build. But there are two important ones for file system checks. One of them is com.apple.rootless.install. That one will basically bypass all file system SIP checks. So if my process has this entitlement, it can basically do what I couldn't do here, right? It can just override all file system protection checks. And com.apple.rootless.install.inheritable is even more interesting, because it actually grants all of its child processes to bypass the file system checks. So if you're able to, let's say, inject to one of these com apple rootless install, then you win, right? You basically bypass SIP. Or if you're able to somehow affect the process with that inheritable thing to create your own child process. So that's exactly what we're going to do here. And interestingly, there have been SIP bypasses in the past. Most of them focus on com.apple.rootless entitled processes. Some of these were very trivial. This was, I don't remember what year, well, 2016. And this was basically a tweetable exploit even, where basically you can create a soft link to a certain file on disk, and then run fsck_cs, which was a SIP entitled binary at the time, to basically override a certain plist file that protects the kernel. So that was pretty interesting and kind of an inspiration to what I wanted to do. So how do you look for SIP bypasses? I had a few examples, a few ideas, sorry. One of them was to examine SIP entitled binaries on my own box, and basically looking for operations that could be exploited by an attacker. An interesting tool to use is there is a database, J's entitlement database. It's always a good way to find entitled binaries, and you can just use that to just start hunting for any entitled binaries, and it will even make a lookup based on the operating system version and so on. And interestingly, you can, even if you have an EDR, and me as a Microsoft employee, I obviously have an EDR, I can just try to hunt for certain things. So I used the EDR itself to look for interesting child processes of once you find an entitled binary, and I did just that. And in this case, you can see ZSH, this guy, with this command line actually spawned from one of the entitled binaries that I found. So in this case, I want to talk exactly about that. System install D. System install D is one of these entitled binaries that I found here. And basically, I started reading about it. And interestingly, it has com.apple.rootless.install.inheritable entitlement. As a reminder, it means that all of the child processes of this little guy will actually bypass SIP file system checks. That daemon, the fact that it ends with a D hints that it's a daemon, and it is a daemon. That daemon gets invoked when installing an Apple signed package. So if you have any PKG file that's Apple signed, it will just start and install it on its own. And that basically kind of answers how Apple updates your operating system and so on, right? Just runs this guy right here. This guy is able to have itself and all of its child processes bypass file system checks and basically bypass SIP by design. And then I started playing with system install D. And System installed, if you look at what it does, you'll see that it does various tasks like updating cache, moving files to temporary files securely. I tried, by the way, and so on. And if a package has a post-install script, it will invoke it. And post-install scripts are run by the shell. And in this case, it was in the package that I found, it was by Z shell. And this kind of explains why I saw ZSH, the Z shell, running under system install D. And then I was kind of happy because I knew that ZSH has a lot of interesting things that it can do when it starts. If you look at ZSH source code, or you know what, before that, I'm more familiar with Bash, and I know Bash RC. So ZSH has a kind of files called ZSHRC, just like Bash RC, and they will run whatever command you give them, but they will only start when you run ZSH in interactive mode. But then I thought closer and even started looking at the ZSH source code, and even if you just look at the ZSH source code, you find these very funny remarks like start a new ZSH and get its default fpath. If some swine has tinkered with this in etc ZSH env, we're out of luck. And then I was like, etc ZH env, what is that? And then if you read about it, you'll see that it's just like ZSHRC, but it runs regardless of whether you run in interactive mode or not. And that's basically kind of funny because it makes the exploit super easy to run. Download a signed package, a PKG file that legitimately invokes ZSH, plant an easy etc ZSH env file. And that file is a 3-liner, right? One of them is just going to look at the parent process ID. If that parent process ID is system install D, then you can do whatever you want without any SIP checks. And that's pretty much it. Once you trigger the installer, you're basically done. And bam, this is exactly what got me the SIP bypass that I reported to Apple. It's already fixed. It was fixed, I think, in October in 2021. And that's a pretty neat logical bug. As a bonus round, ZSH env, besides the etc ZSH env, you have under the home directory .zsh env. And you can use it as a funny elevation of privilege attack. If you run sudo -s, for instance, ZSH does not change the home directory, this tilde right here, and will basically enumerate ZSH env on startup. So that's pretty weird, and I even reported that to Apple, and they said that it was by design, but you can still use it. So basically, you can do the same idea. Just plant a ZSH env file on your home directory. You have to be an admin. Admin doesn't mean root. It's a different thing in macOS. And basically plant the following ZSH env file. If ID-U is 0, if basically means if I'm root, then do whatever you want. This time it wasn't very easy to trigger a root ZSH, but it's cool to just lurk and wait to be rooted. As I said, it's still unfixed, but I want to let Apple and the ZSH community know. A bit of shout outs. After Rootless, my SIP bypass, it was discovered that there are similar issues in exploiting system install D. I think Perception Point did that. It got CVE 2022-22583. In this case, what they did is one of the things that I mentioned is that system install D will drop files in temporary directory securely. So apparently this was secure, but the fact that they drop in /temp was not as secure, because as root you can just remount /temp to your own directory. You have to win basically a race, but basically you can bypass SIP with that, and that's already patched as well. So shout outs to Perception Point that took my idea to the next level, perhaps. Now I want to talk about TCC bypasses. In this case, again, I promised that I do funny vulnerability names, so this one was called Power Deer. What is TCC? TCC is transparency, consent, and control. It's a macOS technology that was first introduced in Mojave. And I see it as the UAC equivalent for macOS. If you're familiar with UAC on Windows, you know what I'm talking about. It's basically whatever wants to control whatever. In this case, Microsoft team would like to access the microphone, and then you have to allow or not allow. And this is controlled from a pane called security and privacy. Here you can see the various access, and there are more, obviously, as you can see from the scroll bar here, there are more access controls than just the microphone, camera, and whatever. But basically, you can allow or disallow or add any apps here. So that's pretty interesting. And TCC is controlled by a database. Interestingly, it's controlled by a SQLite database. So if you're familiar with SQL, just SQL under the hood. And there are two TCC databases. One of them is a system-wide TCC database, and that's the path. The other one is a per user TCC database. So if you have multiple users on the same macOS, each user will have its own TCC database, and it will be just under the same path, but with a tilde mark, basically means your home directory. And TCC is governed by a daemon called tccd. Again, the D stands for daemon. And you'll have two of them. One is for the user and one for the system. And tccd is the one enforcing the policy with the help of another daemon called securityD. And there are interesting interplays between these two daemons. And I want to talk about these two tccd-db files because they're protected. You just can't like access them just without anything like any preparation. One of them is the system TCC database. This one right here is SIP protected, if you remember SIP from 5 minutes ago. So it's protected by SIP. And it's also sandbox TCC protected. So TCC kind of protects itself. You can't just access this file, not even reading it. The user's database is TCC protected. It's not SIP protected, but it's TCC protected. You can't even read with these databases without full disk access. Full disk access is managed by the global SIP protected tccd. So it's kind of like the chicken and the egg problem. In order to write to tccdb, you have to bypass TCC, but in order to bypass TCC, you might want to do some stuff to the TCC database. And it seems that Apple did a pretty good job here, unless you have full disk access, which is kind of a big deal. Sorry about that. A lot of spoilers here. This is an example. This is me trying to list the files under the directory user, my username, library, application support, com, Apple, TCC. And you see that even me running as root, I can't like list files under that directory. It will give you operation not permitted. Interestingly enough, if you guess if you know that the TCC database name is tcc.db, it will let me list it. And that's a pretty neat trick. And I think it was mentioned like more than a couple of times in the history. That's a cool way of knowing whether you have full disk access or not. In a full disk access scenario, you'll be able to get reasonable output from this first line, but second line will always be there. That's a bit about the entitlements of tccd. I did mention tccd as the enforcing daemon for TCC. If you look at the entitlements, you'll see that it has many entitlements. Interestingly, it will have com Apple private TCC allow. That basically means, and TCC service system policy all files. And that's pretty interesting. I did mention in the millionth time this talk, I did mention that entitled binaries are pretty interesting, and tccd is obviously a very entitled binary. And I want to talk about this com Apple private TCC allow entitlement in a sec. A naive TCC bypass. If you do have full disk access, then you can just modify the user's TCC database even without root. That's pretty interesting. If you see here, you'll see that this TCC database, the user TCC database, is owned by me, right? The user, and the user can just write to it. You see the W right here. That basically means that if I have full disk access, but don't even run as root, I'm able to modify the TCC database and basically kind of almost the game over. So you can check if terminal has full disk access. You can deduce that by parsing logs, doing this operation, or by the presence of certain apps. I think that Jamf in the past used to require full disk access to terminal. So if you do have full disk access, you should just write to the TCC database. As a defender, if you guys work for blue teams, you should always watch out for file writes and file reads of the TCC database. That could be a strong indication, if not done by tccd, that could be a strong indication that someone is screwing up with your TCC database. And interestingly, this idea of basically granting full disk access to the terminal and modifying the TCC database was originally abused by Dropbox itself. Just an example. This is me trying to touch the TCC database, the thing that you saw earlier. And if you look at the logs, you'll see that it says handling access request to KTCC service system policy all files from the terminal, and it will just eventually be access denied by service policy. So that's pretty much how you can tell from the logs that TCC rejected or accepted your access, basically. This is how the TCC database looks like. This is, of course, when I do have full disk access. You can see that you have SQLite3. That's basically the tool that I'm using, comes straight out of the box in macOS. And you can just look at the TCC database. If you can see here, I just select everything from access, and you'll see that it has certain rows, right? First one is kind of the TCC access type, if that makes sense. Second one is the identifier of the app, in this case, text edit, and then some numbers, and then certain other things, some question marks, and so on. And we'll get to how this thing is built. Now, this format was changed between operating systems, but I think it's still like that in the latest version. And so what is KTCC service whatever? As you can see here, KTCC service ubiquity, KTCC service system policy, desktop folder, and so on. So as I did say, TCC has fine-grained access, and this is not a complete list by any means, but these are kind of the access names next to the description. So for instance, ubiquity means that you can have iCloud access. Liverpool basically means that you can have location services. Microphone basically means that you have microphone access, and so on. Note that some of them are saved in the user TCC database, and some of them, like the full disk access, the system policy all files, are saved in the system TCC database, which is more problematic to write to because it's C protected, besides the fact that it's TCC protected. For some TCC services, you also have to have a certain blob, and let me see if I have one of them here. No, I don't. But for some TCC services, another blob called csrec is verified, and that's supposed to make TCC database more secure in case code signing changes. So for instance, think that you have an app, it has microphone access, and then someone just uninstalls that app and installs a different app with the same name or something like that. So that's basically kind of an extra verification on the app itself. And that blob encodes the code signing requirements of the app. And interestingly, you can just create your own. That's just an example of how to create a csrec for Teams. And that's basically how you do it. I know it's kind of ugly, but basically running code sign and then basically doing a bunch of strings and feeding them into a binary called csrec will basically give you a binary file that encodes this CS requirement blob. And that's just a little hurdle. But what I'm trying to say is that if you already have code, a way to run code on the box, then it shouldn't stop you from doing anything. I hope that makes sense. Let me just get back to my slide. And I want to talk about the Apple private TCC allow. That's the entitlement that we saw earlier, this time for TCC enablement. As I did mention, private Apple binaries may have entitlements that allow them to bypass TCC checks, just like the game with SIP, but this time for TCC. And this is how tccd can basically touch the TCC database itself, right? And besides the fact that it enforces it, it kind of has full disk access because if you remember from 4 slides ago, it has the KTCC system service policy all files. That's tccd. So tccd is entitled to have this thing, which basically means full disk access, which basically means that it can touch whatever database it wants. So that's how tccd works. And that's an obvious attack surface for TCC bypasses, just like with SIP. Obvious technique: find a binary with COM Apple private TCC allow, tamper with it in some way to affect its code flow, including extensions or whatnot, or inject to it somehow, and get its fine-grained TCC access. So if you find a binary that's allowed to touch, let's say, the microphone, and you inject into it, then you can also touch the microphone without any pop-ups or whatnot. Basically, bypassing TCC for microphone in this case. Interestingly, Apple takes TCC very seriously. If you find a good enough TCC bypass, you can get like big bags with $signs thrown at you from Apple. I'm still waiting for my big bag of money, by the way, if someone from Apple sees this. But basically, this is like documented in the Apple website. So TCC is very serious to Apple. And again, I do admit that they did a pretty good job with TCC. Although there have been TCC bypasses in the past. This is from 2020. This isn't mine. Time Machine is besides a cool thing in the movies, it's also a backup mechanism in macOS. There is a thing called Time Machine where you can backup and restore files. And interestingly, it saves stuff that you can mount later with APFS mount. I won't go into details, but APFS is like the file system, and mounting basically means mounting a file system. Interestingly, time system backups could be mounted with APFS mount with the no owner flag. If you run with a no owner flag, it basically, because it backs up, because the backup contains TCC database, you can read without restrictions by anyone. It basically means that the semantics of the TCC databases are gone. And you can have a single command line to exploit. This is how it might look like. Of course, this is already fixed, but just an example, this is just reading a TCC database, right? And still considered a TCC bypass. Why, by the way? Because if I can read the TCC database, I know which apps have certain TCC access controls. For instance, Teams has microphone, and then I can perhaps piggyback write or something. And this is the thing that I want to focus on today. tccd exploit. This is from 2020. Interestingly, you can, because tccd is, well, regardless of that exploit, actually, this is a pretty interesting thing to note. Because the entitlement is not bound to the binary path, you can copy an entitled binary and it will still stay entitled, right? So this is just a thing to save in your brains. TCC still maintains its original entitlements as they're embedded in the binary, right? So if I copy TCCD to somewhere else, it will still work. One more thing to note, when tccd executes, it will try to find the user's TCC database. Sorry, again. It will try to find the TCC database by expanding the path home, library, application support, com.apple.tcc, and then tcc.db, right? This is for every user, it has its home folder. And interestingly, if you poison the home environment variable, you can basically fool tccd to think that the TCC database is somewhere else, right? And you can basically poison it by launching with launchctl. I won't go into details on why that works, but basically tccd is ran by launchd, and basically you can control the environment variables that launchd provides to its children in some way, in this way specifically. So this is basically how the thing worked. And the idea is pretty cool. Just plant a new TCC database somewhere else, change the home environment, kill TCCD, change the home environment variable to that location, and restart TCCD. And voila, you got a TCC bypass. Interestingly, it was also different TCC bypasses were exploited by malware. In this case, this was in 2021. The malware had a list of well-known apps with certain permissions, just like Zoom has microphone access, for instance. And what it did is to create a bundle inside a donor app. That's how it refers to the app. So for example, applications zoom.us.app/content/macOS/another app, right? So it's like an app within an app. And there was an issue where basically the policy would attribute that to Zoom itself and not to this actual app, and basically, again, piggyback riding on an existing app. So this was kind of funny to see. Apple fixed it already, of course, but just FYI, malware authors always look for these kind of things. And so when I started learning about TCC, I thought, perhaps we should take like this vulnerability, the home directory poisoning, and see how Apple solved it. And the fix was pretty interesting. If you can see here, what Apple did, this is from tccd, just by reverse engineering it, you'll see that it will get the user ID, get the user, well, it's not password, it's basically a password structure that contains all sorts of information, including the home directory. pwdir is specifically the home directory of that user, and basically extract that from there. So what the fix was is to not expand an environment variable, but just extract it directly from the user's information or registration, if that makes sense. So this is how Apple fixed this issue. And in my opinion, it was not good enough. If you look at how get PWUID works, it basically gets the login directory of the user, which can be changed if you have administrator access. So if you have administrator access, you have this command line right here, DSCL, and you can just, this is the attribute that we want to change, NFS home directory, and you can just change it to /temp/whatever, or you can change it to an arbitrary value. So this is what you can do to bypass their fix. And one word about users registration and DSCL. In Apple, in macOS specifically, the user's information is guarded by, I think, is maintained by something called Open Directory, and the way to talk to it is by DSCL. So that's basically the idea here. And this will effectively change this thing right here, which is considered to be the home directory of that user. Apparently, you can't simply call DSCL create, just like I did here, because NFS home directory is hardened. You have to have this policy right here, this TCC policy, and saved in the user's local DB. It's hidden from the UI, but you might still get a pop-up. Note that this pop-up looks kind of benign. It doesn't say trying to bypass TCC or something, but as someone who writes malware, you don't want to have that thing, right? You don't want to have a pop-up. And after some research, I discovered two commands. One of them is ds-import, and the other one was ds-export. And this basically imports and exports stuff to and from directory services. And ds-export was entitled enough, so it won't have this pop-up. So basically, the idea was pretty simple. Export your own DS entry, change the home directory in the file, import it, and you're done. So that was my first exploit, and I sent that to Apple, and they worked on quite a long time to fix it, and they fixed it by accident. Interestingly, when they released Monterey, they changed the entitlement of DS import, and that basically kind of killed my exploit. And it was a happy accident for them. But again, I was looking at other Apple binaries and found this thing, config-d. Config-d is another Apple entitled binary, and it's very attractive because it has com Apple private TCC allow. And interestingly, I won't talk about it too much, but it doesn't have a hardened runtime, and it's extensible. It basically means that you can probably inject to it, and that's basically what I did. And all of the information is here, and basically the exploit was plant a fake TCC database, inject to this guy to change the home directory, kill and restart tccd, and you have a TCC bypass. Shout outs. There are some researchers that did very similar things to do. Regula here injected to the open directories, to the directory services application, for instance, and did something very similar. I think he also has a very cool blog post about it, so check it out. And basically, there are other cool ways of bypassing TCC. Some win by knockout, in my opinion. Some win by points. But TCC is more fragile than it first looks. So you too can look for TCC bypasses, in my opinion. Bonus round. This is something that I started looking at. This is undisclosed, but this is just if you look at tccd and open it with IDA, you'll see that it has very interesting strings like this thing right here. Now, if you don't know a lot about SQL, you can still read about it, but basically this looks like a SQL injection to me. Basically, if you as an attacker control this service name and can inject apostrophes in here, you can probably do a SQL injection to it to inject into the TCC database. So I find that very interesting, and I wasn't able. I only invested it in like half a day or so, but I think this is a very interesting thing to look at if you want to look for TCC bypasses. This is kind of a bonus round for TCC bypasses. Some future research that I'm planning to do, or any future research that you guys might be looking at, sandbox escape. I have a generic sandbox escape. Sadly, I can't talk about it too much, but sandbox escapes are definitely a thing in Mac. Gatekeeper bypasses. There are two awesome ones in recent memory, I think from December 2021, and I should definitely do one too. Kernel bugs. If you're familiar with IOMFB, it's very prone to vulnerabilities, pack issues, and other Apple-specific bugs like the iMessage exploits. They're awesome, and I intend to look at some of the Apple app-specific bugs just to look for interesting things to do. That's pretty much it. As I said, I have some interesting vulnerabilities I just can't disclose yet because I always disclose responsibly, and so should you. Don't drop 0 days anywhere. Some of them are macOS vulnerabilities, other are just Linux or Android and whatnot, and stay tuned. Feel free to follow me on Twitter for more original research. And that's pretty much it. Thank you all for listening and being here. If there are any questions, I would love to take some.
All right. Thank you, Jonathan, for this amazing, informative session. I am sure our participants must have found some important, knowledgeable inputs from it. And everyone, if you have any questions, we will be taking them now. So one of the one of the question is, how come signature will not prevent an app that was changed access to the original permissions?
Can you repeat the question?
How come signature will not prevent an app that was changed access to the original permissions?
Oh, the question about the CSREC blob. So if the app was changed, it's fine. What I mentioned is that, let's say that you have an app, let's take Zoom, for instance. If you have Zoom and it has microphone access, and then I uninstall Zoom and then install a new app that is not Zoom, that has the same name, then it might be a problem, because apps in the TCC database are basically identified by their name. So the extra protection that was added is also to add the signature information about Zoom, right? So you can't just fake that if you have a different, let's say, team ID or stuff that you need. I hope that makes sense. If there are more questions about it, feel free to just chat with me on Twitter or something.
What permissions are needed to change the env var with the tcc.db path? I'm so sorry if I mispronounced it.
Change the environment of what? Can you repeat that again? Sorry.
Yeah, what permissions are needed to change the env space var with the tcc.db path?
Yeah, the environment variable. Yeah. I think the question mixes two different things. Well, to change the home directory, I guess the question refers to the original vulnerability from 2020, 9934. So in order to do that, you don't need to do anything. You just need to basically kill tccd, the user's tccd. You can do that without root, and I think that you can run launchctl and change the home directory even without root, but I'm not entirely sure. This is something that I have to double check. But basically, you don't need. The only thing that you need is to make launchd with launchctl, change the home directory of tccd. And I think you can do that without root. I'm pretty sure.
All right. I think that's all the questions that we have. Others are just comments that your webinar was really amazing and people are thanking you. So thank you, Jonathan, once again, and thank you all for your participation in today's webinar session. You can look out on our social media platforms on any updates on further webinars. And we will be concluding this session over here. Thank you so much for joining. Bye.
Thank you. See ya.